Hi everyone, this is Mrs. Musoff again. So here we're going to do a few more examples talking about how to calculate limits. In one of the earlier videos I talked about finding the limit using substitution and then just supporting your answer with a graph. Well, now for these examples we're actually going to find the limit by graphing first, and then we'll double check it algebraically. And typically algebraically would mean substituting it in. Okay, so for these, I'm going to try and graph these without my calculator. Some of them should be a little more familiar, right, with rational functions. We should be somewhat remembering how to graph those. If not yet, by the end of this lesson, hopefully we're having a pretty good memory of that. And then some of them are going to be a little trickier with the trig stuff. All right, so we'll do one of each just so you can get a chance to see both examples. All right, so in letter A, it says find the limit as t approaches 2 of t squared minus 3t plus 2 divided by t squared minus 4. All right, so here I'm going to determine it graphically first, which means I'm going to first try and graph this function right here. All right, so the function f of x, or sorry, I guess I'll say f of t, equals t squared minus 3t plus 2 divided by t squared minus 4. So that's what I'm going to try and graph first. Now remember, with rational functions, in order to graph them, we want to factor them so that we can see if there is a whole or not. So if I factor this, I'm going to get t minus 2 and t minus 1 in the numerator, and then t minus 2 and t plus 2 in the denominator. All right. When you have a factor in common, like we do here, the t minus 2 in the numerator and the t minus 2 in the denominator, that's what tells you there's a whole. All right, and in order to actually figure out where the whole is, whatever that 0 is, so t minus 2 would be t equals 2. All right, we substitute it into the remainder of the function. All right, so if I were to actually substitute in 2 into the rest of the function, that would say 2 minus 1 divided by 2 plus 2, which would be 1/4. So that means there's a whole at the point 2 comma 1/4. All right, and then the rest of graphing this function is going to come from the remainder function, so t minus 1 divided by t plus 2. All right, so if I want to then look at that function, t minus 1 divided by t plus 2, now I can use that to say, oh, so there's a vertical asymptote at t equals negative 2, the denominator. The horizontal asymptote, because this is the same degree on the top as it is on the bottom, right? T to the first, that means you just take the coefficients of each and divide them. So that'd be 1 divided by 1, which would be y equals 1. All right, x-intercepts are the numerator 0, so that'd be 1 comma 0. And y-intercept is just plugging in 0 for t, or for x, right? So that would be 0 minus 1, that would be negative 1 divided by 2, which would be negative 1/2. All right, so I can use all this information to actually draw my graph. Let's see. There we go. All right, and you'll see drawing this graph is really not too bad. I'm just going to pretty much plot all this information. There's a vertical asymptote at negative 2, a horizontal asymptote at positive 1. And remember, I usually draw those horizontal asymptotes just at the ends because it could cross in the middle. You don't have to do that, though. It's up to you. X-intercept at 1 comma 0, y-intercept at 0, negative 1/2. And then don't forget about the whole. 2, about 1/4, somewhere right there. Right, and hopefully these 3 points here, the whole and the 2 other points, are kind of figuring out how to draw this branch. Right, and on the other side, because this asymptote is just single multiplicity, I know that the other branch will be diagonal from it. But if you weren't sure, you could always plug in some of these x values and see what y value you get. Right, so this is my graph. It says to find the limit as t approaches 2. So as t is approaching 2, that's right here, that's my whole. All right, as I'm approaching 2 from the left, I can see that it's approaching the y value of that whole, which is 1/4. And same thing from the right side. So that means I would say the limit as t approaches 2 of t squared minus 3t plus 2 divided by 2 squared minus 4. That's going to equal 1/4. Okay. If I wanted to confirm it algebraically, that would pretty much be doing substitution. However, if I did substitution in this factored form, we would end up getting 0 in the denominator, which would not be okay. So if I wanted to confirm it algebraically, I would have to use the simplified form, which is the limit as t approaches 2 of t minus 1 divided by t plus 2. Now I can substitute 2 in because I won't get 0 in the denominator, and this is still the same function, we've just simplified it. So this would equal 2 minus 1 divided by 2 plus 2, which again will give us 1/4. Right, so that's confirming it algebraically. So I used the graph to actually find my answer, but then I just double checked it algebraically. Alright, this graph is kind of interesting also, just to give you another scenario. What if we asked you to find the limit as t approaches -2 instead of +2? Then we'd be looking right here where our vertical asymptote is. And since the left side is approaching positive infinity, and the right side would be approaching negative infinity, we would say that limit does not exist. Alright, so just kind of a twist on it, just something to look out for. Alright, if we did the same kind of thing with letter B, the limit as x approaches 0 of sine of 2x divided by x. Now, if you look at this on its own, you should say, I have no idea how to graph that. And that's fair. You don't. Right? But anytime you see trig functions, especially written like fractions here, you should think of the earlier function that we talked about that's going to show up a lot. And that function is f of x equals sine of x divided by x. And in fact, let me scroll over. Right. This function is an extremely important function for you to know and be familiar with, especially what the graph looks like. And if you want to take a look, we can graph it on our calculator real quick, just to remind you. But at some point, you are going to have to know this function without your calculator. It's a pretty basic function. I always think of it as, it's like the sine function, right? But it's getting on towards negative and positive infinity, it gets smaller and smaller and smaller. So it's oscillating, but it's getting smaller and smaller as you move farther away from 0. All right, so to take a look at this graph, I will show you. It's sine of x divided by x. You do need to be in radian mode. All right, and I'm going to adjust my window. I'm going to go from negative 4 pi to 4 pi, just so we can get a broad view. And then my y's, it's actually a pretty small function with y's because we know sine of x always stays between -1 and 1. So I'm just going to do -2 and 2 just so we can see it a little clear. And if I graph that, you can see it's kind of oscillating like a sine curve would, but it gets really big at 0 and then it starts getting small again. So recognizing that graph is going to be extremely important because we see this function a lot while we're doing limits. Okay. So in this, if I were to look at this and say, how am I going to graph this? I would think I want to get it to look something like this because I know what this graph looks like. Well, sine of 2x, maybe you remember slightly that this is a double angle, which means we have an actual identity for double angles. The sine of 2x is equal to 2 sine x cosine x. So what I'm going to do is I'm going to rewrite this limit as 2 sine x cosine x divided by x. And by rewriting it like that, now I can kind of split it up, similar to one of the examples in your notes, so that I do just have this sine of x over x function in one spot, and then I have some other function in another spot. And the way that would look is I would say, okay, I'm going to just take this part out, so sine of x divided by x. And in order to still have it equal the same thing, that means there's a 2 and a cosine x that I'm multiplying by, right? You could write it over 1 if you want, but it's not necessary, just whatever you're comfortable with. Right? Now, using our properties of limits, right, I know that in order to evaluate this limit, I could just find the limit of this function and the limit of this function and multiply them together. In other words, this is the same thing as the limit as x approaches 0 of sine of x over x times the limit as x approaches 0 of 2 cosine of x. Right. And now that I've split it up into these two limits, these should be two graphs that I can draw by hand without my calculator. All right. Sine of x over x, we just took a look to remind ourselves. but that function, it's going to be kind of a wave, right? An oscillating function just like the sine function, but it at 0, at x equals 0, it is at 1, which is its highest point, and then it kind of tapers off towards the ends. All right, so something like that. All right, so this is the sine of x over x function, sine of x over x. And then 2 cosine of x, that should also be a function I'm familiar with because we did graph trig functions earlier. All right, cosine of x, remember cosine starts at the max, which normally is 1. But because the amplitude here is 2, the max will actually be 2. And then we're just approximating. If it goes as high as 2, I know it'll go as low as 2. All right, and it'll do something kind of like that on both sides if I want to show it. All right, so now looking at these two graphs, I should be able to find the limit as x approaches 0. In the graph on the left, as we approach 0, I'm approaching the y value 1 from both sides. So the limit here would equal 1. And in this graph, as I approach 0 from the left side and from the right side, I'm approaching the y value 2. So to calculate my limit, I would say, okay, that means this is going to be 1 times 2, which is just 2. All right. If I wanted to do this algebraically, it would actually be pretty similar to what we just saw in terms of we would have to use the identity, we would have to split it up still. The only difference with doing it algebraically is that at this step right here, I would still convert it into 2 limits, but instead of drawing this graph, I could just plug 0 in for x. All right, so what that would look like is I would say, okay, the limit as x approaches 0 of sine of x over x, that's a limit I should just know, that's 1. And then over here, I would actually just plug 0 in for x. All right, and 2 cosine of 0, that would be 2, so I would still get the same answer. All right, well, hopefully those 2 examples helped make a little more sense of what we'd expect from you with these limits. If you're feeling more confident with it, then go ahead and continue working through that worksheet. I'm going to make one more video with a piecewise example. So if you feel like piecewise functions are something you're still struggling with, then you can take a look at that one. It'll be a little shorter because it's just going to have the one piecewise. If you feel okay about the piecewise functions, then feel free to continue working. And if you have questions, just write them down. All right, thanks for tuning in.